Great, thank you. Thank you for the introduction. As Asunta mentioned, yes, I will present our work on design of a LAMP assay for a specific detection of aster yellows phytoplasma from South Africa. Okay. Firstly, I would like to thank all the presenters that presented their work previously, because they made an excellent introduction to my topic. So I'll be just briefly introduce the background that is relevant for our study. So phytoplasmas in South Africa were firstly discovered in 2006, as Johan mentioned, and they were classified in 16 SR1b subgroup. This is corresponding to Candidatus phytoplasma asteris. There was no diagnostic method available for specific detection of aster yellows from South Africa. So the diagnostic method that they used for the detection of the said phytoplasma was based on a universal three-step nested PCR that targets phytoplasma's 16S region. And furthermore, the need for a detection test that would be applicable for on-site inspections was recognized, so something that can be used in field. So if I recap, there was a need to find a molecular test for specific detection of aster yellow phytoplasma from South Africa. However, it was a bit complicated. The situation was a bit complicated because specific assay design was not possible on classic phytoplasma gene sequences that are normally used for detection of phytoplasma. So there was a need to a novel approach, the genomic approach. The main aim of our study was to develop a LAMP assay that would enable specific detection of aster yellows from South Africa. We actually have quite vast experience with LAMP. We shared our knowledge at the kickoff meeting, and you can check the presentation on the YouTube channel of the Tropicsafe project. However, here we encountered a few challenges because traditional targets were not able to differentiate between aster yellows from South Africa and other phytoplasma strains. We needed a novel approach to get specific targets that would enable us to develop a molecular test. To make things easier, we divided our main aim into three objectives. First was to develop a pipeline for search of specific target sequence within genomic data. The second was to develop a new LAMP diagnostic assay and protocol for the detection of aster yellows from South Africa, and validation of the developed LAMP assay and protocol. We transformed our objectives into a pipeline, if I may use this word here in a broader meaning. And we identified basic steps that this pipeline needed to give us sufficient result that we needed. So the first step of the pipeline was identification of unique target sequences, assay design and in silico evaluation of the designed assay, experimental evaluation of the designed LAMP assays, and finally validation of the selected assays. As mentioned at the beginning, we had to find suitable specific targets that can be used for development of a LAMP assay. And therefore, we needed to start with whole genome data. So our first step, identification of unique target sequences, started with defining a positive data set that consisted of 2 draft genomes of aster yellows from South Africa, and negative data set that consisted of 73 genomes of other phytoplasma and mycoplasma. We implemented RUX program. This is a freely available web-based program that identify unique sequences that are present in positive data set but are missing in negative data set. So we got 802 unique sequences that were present only in positive data set. However, majority of those sequences were actually short and were not useful for designing a LAMP assay. Therefore, we needed to add some quality filtering to get sequences of sufficient quality. We ended up with 11 sequences. So we took those 11 sequences that have had a sufficient quality and put them in the LAMP design process. However, we were able to design LAMP assays only on 3 of those 11 sequences. And furthermore, we implemented some quality filtering and in silico evaluation, and we ended up with 20 LAMP assays that were chosen to be experimentally evaluated. Experimental evaluation is actually quite important in LAMP design process, because in silico evaluation doesn't necessarily tell us what it will happen with those assays in the experimental settings. So even though if assays look very good in silico, they might not perform as well in experimental evaluation step. We used synthetic target and non-target material in the experimental evaluation because natural samples were scarce and hard to obtain. So we did experimental evaluation with 20 selected LAMP assays. However, only 4 of those exhibited desired characteristics, meaning that they were positive on target material and they were negative on non-target material. So there was no cross-reactivity. And all those 4 assays that gave good results in experimental evaluation actually had the same target sequence. So those 4 assays were put in the optimization step that consisted of finding the best suited magnesium concentration, FIP and BIP primer concentration, the best form of the DNA, and if DNA inhibition might be a problem, and determining analytical sensitivity of those 4 assays. So in the optimization step, we found the best performing assay, and that assay was then put through the validation. Validation step was performed on combination of synthetic reference material and real samples from grape wines. And synthetic reference material was used to determine analytical sensitivity of the assay. And we used probability of detection to determine limit of detection of the designed LAMP assay. And the assay had very good limit of detection. Actually, it was able to detect below 10,000 target copies per milliliter of sample. If you are interested more in depth about usability of synthetic reference material, you can find additional information in the technical innovation fact sheets on the website of the project. So in the second step of the validation, we used results on the samples, on the real samples from the grape wines, to calculate performance parameters of the designed assay. And assay exhibited very good performance parameters. It had 100% specificity and very good sensitivity as well. The great advantage of the LAMP as a diagnostic method is that it can be used in on-site settings. It can be used in field. However, it must be paired with quick and simple sample preparation method that also can be used in field, so that it is useful for in-field settings. We tested two different sample preparation methods: crude extract in ELISA buffer and dipstick method. And both methods proved to be very good. They were easy and they paired very good together with our designed LAMP assay. So they gave very good result in the combination with our designed LAMP assay. So if I recap if I recap the main results of the okay.
תשבי פה. שבי פה, שבי פה. נו. You should be able to shout to the phone. Shout to the phone of the people.
Okay, can I go further? Okay, I'm sorry for that. So if I just quickly recap the main results of our study, we showed that genome-informed genome-informed assay design can be successfully used for phytoplasmas. We showed that the synthetic reference material is suitable for evaluation and validation of molecular assays, especially when natural sample material is scarce or hard to obtain. Can you hear me?
No, sorry again. That's a moment there is someone having Yep. Yes. Okay, now we found the intruder. Stella, please continue.
Okay, I hope you could hear the last part. So I will just continue, but if something was not understandable, just please let me know.
Continue. Thank you.
Okay. So we developed and validated a reliable LAMP assay that enables specific detection of aster yellows from South Africa, and the assay can be used for diagnostic and research purposes. Therefore, is useful to find answers to biological questions regarding this phytoplasma. The LAMP exhibited very good diagnostic parameters, especially specificity and also sensitivity. And we included the developed LAMP assay in small test performance study, and it gave 100% concordant result, meaning that it proved to be very specific and reliable and quite robust. If I got you intrigued with my presentation, watch out for our paper that will be published very shortly in plant disease. In that paper, everything that I presented here will be explained more in depth. At the end, I would like to say thank you to everyone that contributed in this study, especially partners from South Africa, and of course our financiers that enable us to do this research. And most importantly, thank you for your attention, and I'm happy to answer any questions. Thank you.